first of all, let me just say it's a great pleasure for me to be able to speak with you, and also to speak on this subject, which is a subject that I enjoy very much, which is the methods for using electronic structure to obtain information about materials, to really learn something interesting about materials based on electronic structure. And BoltzTraP is a tool that helps with that. I miss, of course, visiting in person with different groups, but I'm happy that nowadays with internet, it's still possible for us to communicate and to talk. And so I want to leave time in this webinar for question and answer at the end, or if you like in the middle. I'm not sure how you will interrupt me, but maybe it's possible. And if it is, I'll be happy to. Yeah. I want to also mention Georg Madsen, because BoltzTraP would not exist without Georg Madsen. So I feel like I owe him a lot because of his work on BoltzTraP, and I want to mention him in the beginning. He is a co-author of this paper, and he is the one that really assembled all of this into a good working and usable code. So I wish to thank him. So what am I going to talk about today? So I have a brief menu here on this slide. So first of all, I'm just going to say a very few words about Boltzmann transport in the kind of approximation to Boltzmann transport that's implemented in BoltzTraP. And then I'll talk about how you can use BoltzTraP for different things. So I'm going to start with metals, and I'll talk about plasma frequencies and anisotropy and resistivity analysis, which can be quite useful in understanding metals. If there's experimental data and you can do electronic structure calculations, you can also say a lot about the properties of metals just using some of the quantities that come from BoltzTraP, and I'll say a little bit about that. Then I'll turn to thermoelectrics, which I think is one of the main uses of BoltzTraP, and I'll talk about the Seebeck coefficient, about the transport effective mass, which is something that people often want to know. You often have a semiconductor and you want to say something, what is the effective mass? But the band structure is complicated, and BoltzTraP gives you a simple way to extract a transport effective mass that then you can give. I'll also mention an electronic fitness function, which is a way of screening semiconductors as thermoelectrics based on band structure. And finally, I'll wrap up by speaking about the electronic thermal conductivity and the Lorentz number as it relates to semiconductors. So what do we get from electronic structure? So many of you may use electronic structure codes like Wien2k or VASP or Quantum Expresso or some other codes, and you obtain an electronic structure. And so this is an example of a particular electronic structure. It's for nickel silicide. And what you see is many different bands. These are electronic states. And you have the dispersion of the electronic states in the Brillouin zone. And you see that nickel silicide is a metal because the Fermi energy here is at 0, and you see that there are several bands that cross the Fermi energy. So generally, from an electronic structure calculation, you can obtain the values of these band energies or eigenvalues on a discrete grid of K points. So you would specify some grid of K points, and you will obtain band energies or E of K on that grid of K points. And of course, E of K is a periodic function in K. And for analyzing transport, there's also a band velocity, and the band velocity is the slope of these band dispersions. In other words, the gradient in K space of E of K, and there's a factor of H bar to make it in the right units. And then you know that each state carries a charge, which is minus E. And it also turns out that there's a heat involved, and the heat is the energy minus the chemical potential. And in Boltzmann transport theory, what's done is that one regards the currents as sums over the states with occupations. So each state is regarded as carrying a current. In the equilibrium, there's no net current because the currents of different states cancel. So the basic idea of Boltzmann transport in the relaxation time approximation is that you may have some fields. So fields are things like the electric field, in other words, a gradient of the electric potential, or a thermal gradient, in other words, a temperature gradient, or other fields like a magnetic field. And what these do is they act on the electronic states and they push the distribution function away from the local equilibrium. In other words, local equilibrium means the Fermi distribution. And with the Fermi distribution, you're in equilibrium and there's no current because the currents of different states cancel. But if you prefer some states, for example, due to an electric field, then you change that distribution. So fields push the distribution function away from local equilibrium due to the action on electrons, and then that leads to currents. So that's one term. And the other term is the scattering, which is characterized by relaxation time. And that tends to bring the system back to local equilibrium. And so one obtains a steady state, and that steady state has currents. And so by relating the fields and the currents, one obtains the transport coefficients. So I'm not going to go much more into detail into the underpinnings of Boltzmann transport, but I can recommend some various references, and you can find some references in the BoltzTraP paper for where you can find that information. But a key point, and this is a very important point, is that just like the specific heat, transport only involves states within a few kT of the Fermi level. So that's the Sommerfeld result. And because of that, only a very small part of the Brouwer zone is active. And that's especially true at low temperature. So what that means is that all those states, all those electronic bands that are not near the crossing points with the Fermi energy do not contribute to transport. And so we're going to have a problem. And the problem is that we have a discrete grid of K points, and only a very few of those K points are active in transport. And we still want to do accurate calculations. So here I just give some formulas. These are textbook formulas. And here I'm listing them in a scalar form without the X, Y, and Z, or without the different anisotropic coefficients, but they are tensors in general. And I just list them. So this is the electrical conductivity sigma, and I've written them in the way that you can write them as an integral over energy. So it's written as an integral of sigma v dE, and then sigma v is E squared times this derivative of the Fermi function with respect to energy. That's like a broadened delta function, very close to the Fermi energy. And so just with a width of kT, roughly speaking. And because of that, only the states near the Fermi energy can contribute. And then this quantity is an integral that involves the band velocities, the relaxation time, and the relaxation time. And so the ingredients are going to be the energies, because we need the energies for this derivative of the Fermi function, and also in some of these integrals, and the band velocities, and the relaxation time. Okay, the Seebeck coefficient is a different integral of sigma over E. It's an integral that involves energy times sigma over E, and then it's divided by sigma V, so it's a ratio. And then the closed circuit, and I'll say what I mean by closed circuit later, the closed circuit thermal conductivity is a different integral, and it has the energy squared times sigma V. So in these three coefficients, there's three different integrals, and depending on the band structure, they may be related in different ways. So you can't, knowing one coefficient, say that you know the others directly, though you may have some approximate formulas that help you to understand things. So what does BoltzTraP do? So BoltzTraP tries to solve that problem of only a few points contributing to these integrals. So what BoltzTraP does is it does an interpolation of the band energies, and it's an interpolation, meaning that it's not a fit. It's an interpolation that exactly reproduces the values on the grid. It's a smooth interpolation that lets you take derivatives. That's the key point of BoltzTraP, is it uses this Shanklin method, which is an interpolation that's based on a linear combination of what amounts to plane waves, symmetrized plane waves, which are called real space stars. And then you have an analytic form. It's an interpolated form, but it's exact at the grid points. And it's something that you can take derivatives of to get velocities in an easy and numerically stable way. And it's a smooth interpolation, which means that you don't have wild oscillations between the grid points. So this converges and you can get those derivatives. So BoltzTraP then calculates the velocities using analytic gradients, and it does the k-space integrals of the transport functions on a grid of energy. So that means this function is calculated, and this sigma of E is calculated as a function of E by doing this integral over the zone first. And then you can do all these other integrals by in these other integrals of E. This is integrals with energy, not integrals with K that's already done. And you can do those and get these transport coefficients. So that's what BoltzTraP does. The integrals are done, and this is something that's of interest to some people because they want to modify them. So those integrals that were shown on the previous slide are done in a routine called Fermi integrals.F90. And in that routine, it's assumed that the relaxation time is constant. And if you want to change that, you can, and you have to modify that Fermi integrals.F90. So for example, if you wanted to put in other factors and do other integrals with energy, you could do that. For example, you could put in a tau that instead of being a constant is a constant divided by the density of states. And that would look something like acoustic phonon scattering. And you could modify Fermi integrals to do that. All right, so what about this constant scattering time? So we know that scattering depends on temperature and doping level and many other things, sample details, how many defects are there, what is the nature of the sample. So scattering is something complicated. So what's implemented in BoltzTraP is something called the constant scattering time approximation, and that consists in neglecting the energy dependence of tau and doing the integrals. That doesn't mean that you should neglect the dependence on doping level or temperature or anything else. It just means that the integrals are done with a constant, then you can multiply by the appropriate constant for your problem to get physical results to compare with experiment. For example, if you know that phonon scattering is a key scattering mechanism for your semiconductor that you are studying, then maybe you should that you should take the results from BoltzTraP and then add a temperature factor. And so when you plot things out, you may plot the conductivity from BoltzTraP times a model for the relaxation time that has the correct temperature dependence. So all that BoltzTraP does is it gives you a sigma over tau that's based on an integral that neglects the energy dependence of tau. Okay. So what does that mean? That means if you want to analyze sigma, the conductivity, well, sigma over tau is what comes from BoltzTraP. So you should multiply by tau, and there you can put in some functional form for tau. The Seebeck coefficient is a ratio. And because it's a ratio, tau cancels in the constant scattering time approximation. And that's very convenient because then you can directly compare it with experiment. And the same thing is true for the Lorentz number, because the Lorentz number is the electronic thermal conductivity divided by the electrical conductivity times temperature. And that also is a ratio that can be directly calculated with the constant scattering time approximation. And now I said I would say something about what I meant by this closed circuit thermal conductivity. So what is important to keep in mind is that electrons carry both heat and charge. And so a thermal gradient induces electron flow. So if you have a material and you allow electrons to flow, if you say that my boundary condition is that there's no voltage and that there's a thermal gradient, what that means is that there'll both be an electrical current and a thermal current carried by electrons. And so there'll be both a charge current and a heat current. So BoltzTraP calculates this case. So this is the case where there's no voltage. There's two different temperatures and there's no voltage difference. But a common experimental condition for measuring thermal conductivity is to do open circuit. And then no charge can flow. And instead there's a Seebeck voltage that stops the charge flow. And this also affects the thermal conductivity because if you impede the flow of electrons, then you also affect the heat that the electrons can carry. And that gives a correction to the thermal conductivity that needs to be thought of when you compare with experiment. So that's this kappa E open. That's the open circuit one. And that's equal to the kappa E that BoltzTraP calculates minus a correction term that looks a little bit like the power factor times temperature for a thermoelectric, sigma S squared T. And that's usually a small correction, but it's important in thermoelectrics, and it's especially important when the Seebeck coefficient is high. That means at low carrier concentration. But in either case, the Lorentz number is a ratio that can be calculated directly with the constant scattering time approximation. So now I want to, so I think that's enough about formality because, you can look in the papers and find those formulas and you can see more details about them. But I think I said the important things. And now I'd like to talk about how you can use BoltzTraP to get physical insights into the behaviors of materials. So let's start with metals. So let's just say you have a metal and you calculate its Fermi surface, because we know that transport is associated with the Fermi surface. So what's being shown here is the Fermi surface of a certain superconductor that I studied many years ago. It's one of the parent superconductors of the iron-based materials. It's lanthanum, iron, arsenic, oxygen. It was the first high TC iron-based superconductor when doped. And so we and other people calculated electronic structures, and this is a picture of the electronic structure. It shows the Brillouin zone. Here it's shown a little bit unconventionally because that's how that paper showed it. With the gamma point, the zone center is on a corner of this plot. But never mind about that. We want to say something about the transport in that material. So what you can do is you can apply BoltzTraP, and the first thing you could do is calculate the transport anisotropy, because the conductivity, as I showed it, depends on the velocities. It's a product of velocities that goes into sigma V, and that gives you the anisotropy of sigma. So sigma alpha beta is a rank 2 tensor with the crystal symmetry. And so if we make the constant scattering time approximation, which BoltzTraP does, then you put in tau as a single scalar number, then the anisotropy of sigma over tau from BoltzTraP gives you a prediction of the conductivity anisotropy of a metal, and it's often quite good. So the prediction for this material that you got from BoltzTraP was that that ratio was 15, and that was an important physical result because that was lower than most cuprate high temperature superconductors, and that has implications for making conductors, superconducting conductors for applications. Another thing you might be interested in is collaborating with somebody who's doing optical measurements, and they might be doing infrared measurements. And so they might measure a plasma frequency from infrared measurements. And that's related to the conductivity. So this is an example. This is another one about iron-based superconductors. And what happened here was that an experimental collaborator did measurements, infrared optical measurements of reflectivity. And from those measurements, they extracted a plasma frequency. And we can easily get the plasma frequency from BoltzTraP. Then you can compare that with experiment, and the renormalization may tell you something about fluctuations and also about correlations in materials. And this plot is just showing a characterization of that. The horizontal axis in this plot is the renormalization, with one being non-renormalized. So from BoltzTraP, what you get is a sigma over tau, but h bar times the plasma frequency is h bar times the square root of sigma over tau times the square root of 1 over the free space permittivity, epsilon 0. And so the free space permittivity is a known number. And so you take the calculated sigma over tau from BoltzTraP, you take the square root and multiply the numbers, and then you get the plasma frequency. If you multiply by h bar, then you can get it in the right units and compare it with experiment. Finally, in metals, people often don't think about thermal power, but thermal power is actually a very useful probe of the Fermi surface of metals as well. So this is the Fermi surface of platinum cobalt oxide. It's a very high conductivity delaphosite material, and it's very two-dimensional. It means that the conductivity is extremely anisotropic. I talked about anisotropy of the conductivity a couple of slides back. This material has an extremely high anisotropy, but it depends on energy. And so the result is that the Seebeck coefficient can be quite interesting, even though it's a metal. So what we did was we calculated the Seebeck coefficient of this metal. So you don't often think about Seebeck coefficients of metals, but there is a number. It's a small number usually, so not useful for thermoelectric devices, but still physically interesting and measurable. And so what we found was that in plane, in the high conductivity direction, the Seebeck coefficient is what's expected, small and not very interesting. So this is SXX on this plot. And we did two different materials. The other material is palladium cobalt oxide, which is also a delaphosite. But in the perpendicular direction, the c-axis direction in this material, the Seebeck coefficient is extremely large, and it has a different temperature dependence. It saturates and becomes flat and relatively temperature independent. And so this was telling something about the energy dependence of this electronic structure, saying that it becomes more three-dimensional as you move energy away from the Fermi energy. And that was a difficult quantity to confirm, but it was finally experimentally confirmed recently in this paper. And it revealed something interesting about the electronic structure of that material. That material is regarded as a very unusual material from the point of view of transport for some other reasons that I'm not going to speak about. And then finally, and I think this is something that's not done very much, but a lot could be done with it, is just using BoltzTraP to analyze resistivity of metals. So this is combining theory and experiment. So if you have experimental collaborators who measure resistivity, they may be quite interested in this type of interaction. So this is a plot. This is a certain material, potassium, cobalt 2, arsenic 2, but it's a certain metal. And what's being plotted here is the resistivity in microohm centimeters versus temperature. And you very often find things like that in experimental papers. So what can you get from that? So what it shows is that low temperature in this particular material, it's quite small. It's a very good conductor at low temperature because they made very clean crystals of it. Then there's a region where it curves upwards, sometimes parabolically, but maybe not. And then there's typically a large region where the resistivity is approximately linear with temperature. In this material, there's a slight upward curvature, which is anomalous and is interesting, but I'm not going to discuss that. But in many metals, what you see is a large temperature range where the resistivity is approximately linear with temperature. That's a very common behavior. And then maybe at high temperature, it saturates. And that's an interesting behavior, but that's not the one I'm speaking about. I'm talking about this kind of quasi-linear regime that you often see. Now, the resistivity depends on two things. It depends on sigma over tau, which in a metal is very weakly temperature dependent because you're not near a band edge or any other structure typically. And then relaxation time tau, which is what we want to understand. So if you took this resistivity, you could extract tau if you knew sigma over tau. That's a clear statement, I think. But you can do more than that. So there's a paper. This is a work of Phil Allen from Stony Brook. There's a paper from 1987 where he shows how you extract electron phonon lambda values from the resistivity of metals. And it's a rough formula, but it's a useful formula. So there's a formula for connecting the electron phonon, or in fact, other bosonic coupling. So it could be electron magnon or something like that, coupling to the resistivity. And so this is the formula that was given in that paper. Lambda transport is h bar omega p squared rho over t times some function, and that function is about 1 at high temperature. It's approximately 1, divided by some other fundamental constants. And so if you know omega p squared, I showed you how to get that from sigma over tau, and you know the resistivity over temperature. This could be the slope of the resistivity. So here you could put d rho dt for rho over t. Then you could extract the value of lambda transport. And what's interesting about that is you can compare that with other experimental measurements for the metal. So you can get this coupling lambda transport, but that could be related to the specific heat enhancement, lambda gamma. So if they did specific heat measurements, which very often experimentalists do, there's a experimental specific heat gamma, which is 1 plus lambda, maybe a different lambda, times gamma bare. Gamma bare is the density of states gamma from your electronic structure calculation. And so then you can get some information about what the electron phonon coupling is. And that also can be related to the electron phonon coupling lambda used in superconducting properties, and some interesting physics can be obtained from that depending on the material that you are studying. So I think that's enough of metals for now. And I would like to now go and talk about thermoelectrics. So I think this is one of the main uses of BoltzTraP, is to study thermoelectric materials. So a thermoelectric device is a semiconductor device. There's a material-specific figure of merit, and that's a combination of electrical and thermal transport coefficients. Zt is sigma s squared t divided by the thermal conductivity. And BoltzTraP is about the electrical components of those transport coefficients. So the important thing to remember about thermoelectrics is that we have this composite property that we're trying to optimize, this Zt. And I think it's fascinating that Zt is a contraindicated property of matter. What that means is that within simple textbook models, you never expect to find high Zt. Why is that? Well, several things have been discussed. So the first thing that's been very much discussed is you want high conductivity and low thermal conductivity. So you want scattering of phonons to get low thermal conductivity, but high mobility, meaning little scattering of electrons. And there's lots of discussion around that. It's not the main subject of this talk. Something else is high conductivity and high thermal power together. That means high Seebeck coefficient and high sigma. And that doesn't happen in simple parabolic band models. And so complex electronic structures are thought to be important for obtaining this. And then there's other contradictions. But that makes thermoelectrics very interesting, because that means you look for unconventional materials. And materials that are unconventional in one way, that means in the way of showing high Zt, may be unconventional in other ways as well. For example, there's a large connection between thermoelectrics and topological insulators through complex band structures. So just to be a little bit more specific, in textbooks, you find the single parabolic band model. That means free electrons. And so that's the formula that E is h bar squared k squared over 2m, which is the same as the introductory physics formula, P, energy is p squared over 2m in classical physics. And the result is that the density of states looks like the plot in this lower panel, where the density of states is proportional to the square root of E. And you have a conundrum, because as you saw in the transport formulas, light mass will mean high band velocity because the slope will be high and therefore the conductivity will be high as a result, so high conductivity. But you saw that a derivative was important for the Seebeck coefficient through that energy factor in the integral that enters the Seebeck coefficient. And so heavy mass will favor high thermal power. And you can't, you would say, have light mass and heavy mass at the same time. And so some resolution to that conundrum must be found. And the resolution is in complex band structures of various types. So if you look at gallium arsenide, for example, if you look at p-type gallium arsenide, you see already, look at the valence bands, you see already that there are light holes and heavy holes, and exactly how light and how heavy depends on what direction you go in, even though the material is cubic. And so that's a kind of complexity of the band structure, and so things could be more complicated. And the other thing about thermoelectrics is you need to optimize. And so that's well known. This is from a textbook by Joffe from 1957. Alpha is the Seebeck coefficient in this textbook, and sigma is the conductivity. And the idea is that the Seebeck coefficient decreases with doping and the conductivity increases with doping. And so the term in the numerator of ZT has a maximum at some doping level, and it's important to find out what that doping level is and to synthesize samples there. And synthesizing samples is expensive and time consuming, so theory can certainly help, and models were often used, such as parabolic band models. And now with BoltzTraP, you can do predictive theory and do a better job of that optimization. So I want to illustrate that by speaking about lead telluride, which is a known good thermoelectric material that shows high thermoelectric performance, nowadays approaching 2. So it has the rock salt crystal structure, so it's fairly simple. It's a narrow gap semiconductor. And so we can hope to not only calculate things, but also get some understanding of things. So this is relatively old work now, but this is the band structure of lead telluride. And I'd like to focus on the region near the band gap. The band gap is here. The valence band maximum is at 0 electron volts, and there's a small band gap and then a conduction band. And what you see immediately by just looking at this, look at the L point, is that this is not an isotropic parabolic band system, because you see that the dispersion in this direction towards W and the dispersion in this direction towards gamma are different, and the bands do not look parabolic. And you also see that in the density of states. So this is the p-type density of states, starting at 0, which is the valence band maximum, and then going down in energy away from the band edge. And what you see is that it's very low, which is characteristic of a light mass, which you might think would give you high conductivity. And then at some binding energy at 0.2 electron volts, it becomes very high and steep, which you would think might do something with the Seebeck coefficient. And the reason is that if you plot the carrier pockets, you see that they reconnect at around 0.2 electron volts, where that onset was, from these small carrier pockets around the L points of the FCC Broma zone to interconnected pockets with these tube-like interconnections. And you see that these tube-like interconnections are not anything like spheres that would be characteristic of a parabolic band. So the band structure is unusual. So this is what you can do with BoltzTraP. So this is what we did with BoltzTraP. So you can calculate the Seebeck coefficient as a function of temperature and as a function of doping. And so these are the curves. And so this is the constant scattering time approximation. So no experimental data other than the crystal structure went into this. So what was done is to take the crystal structure, obtain the electronic structure, run BoltzTraP with the constant scattering time approximation, and plot out the results. That's all. So you get these curves. At around that time, it was reported that very high ZT could be obtained in thallium-doped lead telluride due to perhaps some changes in the electronic structure. But this is just lead telluride. And we calculated the Seebeck coefficient. And what we found was that, first of all, it looks unusual, but you might expect it to look unusual because the band structure is unusual. It's not a parabolic band system. So you don't expect it to look like a parabolic band system. And what's unusual is that if you look at these three different doping levels that are shown by these three different lines, those are quite different doping levels. The three lines are very close to each other, whereas you expect in a parabolic band system that the Seebeck coefficient will fall rather more strongly with doping level. But in any case, this was similar to the experimental data for the thallium dope system. So we were able to predict that if you could sodium dope or do some other doping to levels that were similar to what was reported in the thallium dope system, then you may also obtain high ZT, which would be interesting because thallium, while it might be favorable for the thermoelectric performance, is a toxic material and is undesirable in applications. So we made that prediction in this paper, and that was what the group of Schneider and coworkers obtained when they tried it with sodium doping, perhaps because of a change in electronic structure, but they found that lead telluride with sodium doping at very high doping levels, the ones similar to those that we studied, can in fact have very high ZTs compared to the thallium. So even though the constant scattering time approximation is clearly an approximation, the fact that it's predictive, meaning it doesn't require fits, allows you to make useful predictions that can be tested experimentally. So a key point in lead telluride was the fact that the electronic structure was unusual. In other words, the band structure was not a parabolic band structure. And often that's the case in thermoelectrics, that you're looking for things like that. And you would seek materials that have high ZT, but you would understand that the isotropic parabolic band, single parabolic band, may not be the optimum band structure for that. And you may be looking for other kinds of band structures, and you'd like to be able to compare different materials in order to make predictions of materials that experimentalists might like to investigate. So I'm just showing here some pictures of isosurface. These are carrier pocket visualizations for different materials. So this is bismuth telluride. It's a topological insulator. This is also p-type. And you see this very complex electronic structure. And bismuth telluride is probably the best room temperature binary thermoelectric material that's known. These are some other materials. So this is about complex shapes of isosurface carrier pocket complexity. So you can find materials like that. Another feature, electronic feature that has been associated with high thermoelectric performance is the idea of having multiple carrier pockets. So this is magnesium 3 antimony 2, N-type magnesium 3 antimony 2, which is a newly discovered thermoelectric material, a very good one. And what you see is multiple carrier pockets in the Brillouin zone, multiple anisotropic carrier pockets. So that's a kind of a band complexity. Another one is a band convergence. This is from work of Jeff Schneider and coworkers. So this is about the magnesium silicon tin system. And here, depending on which endpoint compound you're at, there you have a certain ordering of the conduction bands, and that ordering changes as you go from silicon to tin. And at some point in between, you could infer that they cross, and that was called band convergence. And that's another complex electronic structure feature that was associated with high thermoelectric performance. This is another such feature. So this is silver bismuth selenide. And for N-type, it's predicted to have these very complex anisotropic carrier pockets, multiple carrier pockets. And that also is a feature that can give you high ZT. And then sometimes it's not just about carrier pockets, but it's about band position. So this is a P-type scutterudite material, and this is lanthanum telluride and N-type. And in these materials, you have a light mass band and a heavy mass band that are in proximity. So here's the light mass band, and here are some heavier mass bands. And so if the Fermi energy is somewhere near there, then you can get an enhancement of the Seebeck coefficient that can give you an enhancement of ZT, depending on the positioning of the Fermi energy. So the real question is, we can calculate electronic structures. But supposing we calculate many electronic structures, then how can we know which ones are the better ones from the point of view of thermoelectrics? Ideally, we would like to have a number. We'd like to have some number that would tell us the extent to which this is a good band structure for thermoelectrics. And so what do we mean by a good band structure for thermoelectrics? So we're interested in conductivity and Seebeck coefficient, and we saw the problem earlier on that these two things are coupled in a parabolic band model. So high S means low sigma. High sigma means low S. But if we have a complex band structure, maybe we can have both. And so what we really want to know is, given a band structure, could we tell if that band structure will enable sigma and S to both be high? So we're not trying to get an effective mass. So we want to have a screen, and we want to have a practical screen that we can apply. What we know is that BoltzTraP allows us to do the transport integrals that go into those coefficients. It doesn't allow us to calculate directly the relaxation time. And so we decided to adopt a heuristic and see how that would work. So we just wrote down some functions and tried them. And then we settled on this function, which we call the electronic fitness function. So the electronic fitness function, T, is the idea was to have something that you get directly from BoltzTraP, and that can quantify this decoupling of sigma and S. So the electronic fitness function that we defined is sigma over tau, that comes directly from BoltzTraP, times the Seebeck coefficient squared with the constant scattering time approximation, that comes directly from BoltzTraP, and then divided by the density of states to the 2/3 power. And the reason for that is that we wanted a factor that would say that high density of states tends to reduce the relaxation time. In other words, it leads to higher scattering, and there's various mechanisms for that. Electron phonon scattering is one such mechanism that would lead to reduction. We chose the 2/3 power empirically, and then we said, instead of just density of states, we said volumetric density of states. That means density of states per unit volume. And the reason for that is we didn't want it to be that if you doubled the unit cell, you would get double the density of states, because that's not physical. So this is what we wrote down for this electronic fitness function. And then we tried it. We applied it to some different materials, thermoelectric type materials. And what this plot is showing is a plot of the experimentally measured best ZT for different materials. And on the horizontal axis, this fitness function calculated at the same temperature as the experimental measurement with the carrier concentration optimized. In other words, choose the carrier concentration that gives the highest T for the given temperature. And what you see is that even though this doesn't even include the lattice thermal conductivity, it gives a correlation. And so, the correlation is not perfect, but it does give a correlation. And because of this correlation, then we could say high electronic fitness function is one property that would indicate that a compound might have high ZT. So that's as far as we can go with that. The key point is it's easy to calculate this electronic fitness function. So you can apply it to many band structures easily. And I wrote a small code that calculates that plus the transport effective mass. And this website at the bottom gives that little code that you can obtain and then use with BoltzTraP to obtain this electronic fitness function. So how do you do that? So how do you calculate the transport effective mass and the electronic fitness function? So you run the first principles electronic structure, then you run BoltzTraP, then you run this little code, and then the outputs are doping level and temperature dependent electronic fitness function and transport effective mass. So what good is that? So maybe you want to see some examples. So I thought I would just show that. So one example is P-type germanium telluride. So you can calculate anything you like. So you can calculate germanium telluride, and you can also calculate crystal structures that don't exist in nature. So what is being shown here in the top is this electronic fitness function as a function of carrier concentration, P-type, for some different materials. Lead telluride, which is a known good thermoelectric material, tin telluride, then rhombohedral germanium telluride, which is the actual crystal structure of germanium telluride at 600 Kelvin, and then cubic germanium telluride, which is the crystal structure of germanium telluride, but only at higher temperature, not at 600 Kelvin. So this is just showing that there's a phase transition in germanium telluride, and at 600 Kelvin, you're in the low temperature phase. But never mind that. If you do it, then what you find is that is in a certain carrier concentration range, a very heavy carrier doping level actually, germanium telluride, cubic, has a much higher electronic fitness function than the other materials. And so you would think this could be a very good thermoelectric. It has other problems. Germanium is a very expensive material, for example. So not only can you do that, but you can analyze that. So both rhombohedral and cubic germanium telluride have complex electronic structures. So rhombohedral germanium telluride, I'm not going to walk you through this in the interest of time, but you can see these projections. This is as a function of carrier concentration or Fermi energy, if you like, for rhombohedral germanium telluride. You see this band convergence that leads to these quite complex looking carrier pockets that should be quite favorable for thermoelectric performance. And the cubic, you see these very small, that means light mass, but very anisotropic carrier pockets. Remember, multiple anisotropic carrier pockets is also favorable, and they reconnect at a certain binding energy similar to what I showed you for lead telluride. And this is a plot, a kind of busy plot of the densities of states, and you can see that rhombohedral and cubic germanium telluride, that's this curve for cubic, and this one for rhombohedral, are very different, and the rhombohedral has quite a low density of states and then a strong onset. And so you can explain why the electronic fitness function for cubic germanium telluride would be high. Anyway, we were fortunate to have experimental collaborators. So this is the group of Zifeng Ren, and he decided for different reasons to try to stabilize cubic germanium telluride down to low temperature. For this purpose, he found that manganese was a useful addition, and And he added quite a lot of manganese. These are X equals. So this means X equals 0.1 means 10% replacement of germanium by manganese. So that's a very big replacement that would affect, you would expect to have a very detrimental effect on the mobility. But nonetheless, what he found was that these samples have very high ZTs down to lower temperatures, 600 Kelvin. So this is still cubic because it's stabilized cubic by the manganese, so it never shows the rhombohedral phase. And then continues to be high down at lower temperature, which is a very favorable feature for waste heat harvesting. So it's a good material. So you notice these numbers. This is 1.5. All right. So the last topic that I want to talk about is the electronic thermal conductivity. So the thermal conductivity is a very important parameter for thermoelectrics. Notice that it's in the denominator of ZT, and it's typically written as the sum of electronic and lattice contributions. That's an approximation. It ignores the coupling of electron and phonon transport. So if there's a strong electron-phonon coupling, then that's an approximation, and there's other things that you need to think about. But in any case, it's typically written that kappa is a lattice term, kappa L, plus an electronic term, kappa E. And it's often desirable to analyze and optimize these separately from an experimental point of view, because, for example, one will depend more on doping than the other. And there's a Wiedemann-Franz relation for the electronic part that says that kappa E is L sigma T, where L is the Lorentz number. So Lorentz number for a metal, for a high carrier density metal, has a classical value that's roughly true in most materials. It's 2.4 times 10 to the minus 8 in these units. But in thermoelectrics, it can be different, and you would like to know what it is. So electrons carry both heat and charge. Electrical currents also carry heat. And so the electrical boundary conditions, as mentioned, can be important. So the formula implemented in BoltzTraP is for the closed circuit. So this is the formula that's implemented in BoltzTraP. Okay, this you saw before. And in this case, there's also a current. The open circuit case, which is what's often used for thermal conductivity measurements, is different because of this factor that I mentioned. And so if you want to compare with experiment, you need to think about this factor. And that difference could be large if S is large. The Seebeck coefficient is large. And that's the case in lightly doped thermoelectric materials. So this is just showing that. So this is magnesium antimony at 500 Kelvin. And this is from a paper. So the plots are a little complicated because there's from different figures in the paper, but it's illustrating that fact. So this is the Lorentz number without that correction, so the closed circuit case. So it's showing two different approximations, constant scattering time approximation, which is what comes out of BoltzTraP, and then a modified BoltzTraP with the Fermi integrals routine changed to have an acoustic phonon scattering model. But let's focus on the constant scattering time model. That's the blue curves. And what you see is that when you go to low carrier concentration, the Lorentz number increases, and that's due to bipolar conduction. This is now only for p-type. If you do the same thing with that correction term, the open circuit case, then you see that actually the Lorentz number for that open circuit case is actually lower than the classical value of 2.4 instead of higher. This is the classical value of 2.4 on this plot. Notice that the scales are different. And so that's an important thing. Experimentalists often use a formula L equals 1.5 plus this exponential that involves the Seebeck coefficient. And that's a different formula, and it's not exactly the same as the result from BoltzTraP. So that formula is this. The BoltzTraP result is this. It's a lower number. So the Lorentz number is significantly different between those two. So why do experimentalists use this? The reason is this is all things that can be easily measured. So S, you can measure the Seebeck coefficient, and then you can get an L, and then extract an electronic thermal conductivity, and then the remainder would be the lattice thermal conductivity that you can analyze. But if you have access to band structure and use BoltzTraP, you can extract a better value of L that can help you to do a better job of extracting the electronic part to then have a lattice part to discuss in the context of experiments. So that's all I wanted to say today. I wanted to try to finish up on time. I think I'm approximately on time and leave some room for discussion. So BoltzTraP is a tool for interpolating and analyzing band structure. So BoltzTraP is working on the band structure part, the eigenvalues, the velocities, and then doing integrals. So it produces transport-related information using the constant scattering time approximation, which you can modify. It gives you a predictive parameter-free calculation of the Seebeck coefficient and the Lorentz number, which can be useful in comparing with experiments. It can also be used in metals for the plasma frequency, conductivity, anisotropy, and resistivity, and in thermoelectrics for several different things that we talked about. So thank you very much for your attention, and thank you especially for listening to me and giving me a chance to speak about BoltzTraP, which is a subject that I very much enjoy speaking about. Thank you.